This is Algebra Lesson 9.5, Solving Exponential Equations. So we are going to use a fancy thing called a logarithm to help us solve exponential equations. I think so far if we've done any, we've done a little guess and check, or we've done it recursively, where you can hit enter and count as you go. But if you want to find that answer without having to do one of those methods, guess and check or recursively, we use what's called a logarithm. And logarithm is kind of the opposite of power of x. But a logarithm with a base of b of a equals x translates to whatever your base is to the power of x equals your answer. And so if we have an equation in exponential form, we can use the change of base property here. It would be the log of a divided by the log of b to solve that answer for us. Now that looks weird, but if you're okay with solving linear equations, then you'll be fine with this. We do need to make sure we have a calculator that has a log button. I don't know if this one does. I saw it at the bottom, but I still want to use my graphing calculator. If you have one of the little blue calculators that I have in my classroom, this one has a log button too. And the log button on the little blue calculators is right underneath the second button. Mine's a little further down, but on the blue calculators, it's in the top corner right under the second button. So let's go with solving this. What we're going to do to bring the x out of the exponent is throw some logs on. So if I add a log in front of the 5x, the x is no longer a power of x, it's a normal sized variable x. But whatever we do to one side of an equation, we always have to do the other side to keep it balanced. So if I throw a log on this side, I also need to throw a log on this side. I'm going to write some parentheses in here because that's how it's going to show up on your calculator screen, just so that it looks the same. So by adding logs to both sides, keeping things balanced, I'm able to take the x out of the exponent and make it a normal variable x. So just like with a linear equation, when you have a number in front of x, we divide both sides by that value to undo that multiplication. So I'm going to divide by the number log 5. We're doing the same thing on both sides of the equation, divide by the number log 5. Log 5 cancels with log 5. X is our variable then, and we would use our calculator to type log of 228 divided by log of 5. Make sure you use the parentheses just like I wrote them. If you don't close that parentheses after the 228, your order of operations will read this incorrectly. My answer then is 3.37. And it's always good practice to check your work. Nope. There we go. If I do 5 to the power of 3.37, I should get an answer pretty close to 228. I got 226.7. It's a little low, but it's because I rounded that value. If I keep more decimals, it'll be much more accurate, but there really isn't a need for that many decimals. But you can see now we're getting really close to the right answer. Next one, we're going to solve this one. This is our typical exponential form. We have our starting value of 4. Our rate of change is a 12% increase, and we want to know when are we going to reach 46. So I'm going to solve this by dividing both sides by 4. That gives me 1.12 to the x equals 11.5. Now I need to throw some logs on. I'm going to add log on this one, and now my x is no longer a power, but a normal variable-sized x, and we throw logs on both sides to keep it balanced. Remember, log is a number, so I'm going to divide by that number, log 112. Numbers cancel out. Divide by that number, log 112. And I can type that one in the calculator to get what my power would be. That is log 11.5, close the parentheses, divided by log 1.12. And I got 21.55. Again, I like to check my answer. So that looks like 4 times 1.12 to the power of 21.55 should be pretty close to 46. And I got 45.99. I think if I had kept more decimals, I would have gotten even closer, but that's very close to me. Okay, we got one left down here. Write an exponential equation to model the situation. We have an initial deposit of $500 invested at 8.5% interest compounded annually. So we have our starting value. We're going to have to do our side calculation to get our ratio. If we start at 100% and we add 8.5%, that brings me to 108.5%. Convert that to a decimal. You can hit your percent button. Divide by 100. Move your decimal 2 spaces. They all do the same thing. I have 1.085. So y equals starting value. My ratio 1.085 represents my 8.5% increase to the power of x. How long will it take the balance to grow to $800? So I'm going to plug $800 in for my y value. I'm going to write my equation equals 800. And we'll solve this the same way that we solved example A part B. Two-step solution, divide both sides to get rid of that 500, and then log both sides to get rid of the variable power of x. $1.085x equals 246, 1.6, and I'm going to add logs on both sides. And what that does is make my x a big X, no longer a power x. And let's just squeeze that log right in here. So we're going to divide by the number in front of x. We're going to divide by log 1.085. Divide log 1.085. And on my calculator, log of 1.6 divided by log of 1.085 tells me it'll take approximately 6 years for that savings deposit to mature. That is it for my notes. Good luck on the exercises, and please let me know if you have questions.